Good afternoon, everyone. Welcome to this Pint of Science event at the University of Greenwich. I am Panos Klukinas. I'm a senior lecturer in civil engineering, and I will be your host for this evening. So you know who am I, but we don't know who you are. So feel free to use the chat and drop us a line with your name and where you're watching from. And you can also use this chat throughout the whole presentation to drop your comments and questions anywhere you like to show us what a passionate audience you are. This will be extremely helpful for our speakers to feel like there is a live audience in front of them so they can give their best. You will also have some opportunities for live interaction with the speakers during the presentation through a special platform called Mentimeter. You can see this on the screen, where you can log in using this code, and then you can participate in opinion surveys and answer questions and send your answers to the speakers so they can comment on that. Before we start, some essential things first. I'm sure that you will not be able to leave your seats during this 1 hour flight. So now is a good time to go and fill up your pint or half pint. Ideally, grab a glass from your favorite fall festival just to get you into the mood. Fill it up with your favorite drink or soft drink and sit back, relax, and enjoy this evening. Let me go straight into the topic. What we have prepared for you tonight, we have two members of our civil engineering dream team who will travel you through the magic world of earthquake engineering, and not only earthquake, because they will take you off beyond the boundaries of Earth. You see, for us in civil engineering at Greenwich, the sky is obviously not a limit at all. So you'll have the opportunity during this hour to travel around the globe, but also on Moon and on Mars, and discuss about natural hazards and safety of structures and human settlements. So no more waiting. I will introduce now my two amazing colleagues, two superb engineers and researchers, experts in earthquake engineering. First, let's welcome on board Dr. Marianna Ercolino.
Hi, Panos. Good evening, everyone. Thank
Hi,
you very
Marianna.
much. Your introductions are always great. Thank you.
Let's show the same excitement welcoming on board Dr. Georgios Kampas.
Hi, Panos. Thanks a lot for the great intro. Hi, everyone. Hope you enjoyed this as much as we, and cheers.
Are you ready to amaze us?
Yes, we are.
Of course.
I was not expecting anything less. So let's show again the Mentimeter platform as I'm stepping aside and leaving the floor to Marianna. So this is the website, no account or sign in required. Just type this 8-digit code and you are in. Marianna, the floor is yours.
Thank you again, Panos. So good evening again. Thank you very much for joining us in this Pint of Science talk tonight with Georgios. So today, actually, we want to show you what we do as a daily job as civil engineers. And also we want to show you the greatest challenges we have to deal with when we talk about structures. So civil engineering is a discipline that is mainly looking at design, construct, and maintain any type of systems that we call built environment. So we look at buildings like houses, offices, but also we look at public, infrastructure like tunnels, like bridges, and pipelines. So when we actually say that we are designing these structures, is actually it's all about finding the optimal solutions for our users and for our clients. So to give an idea what we do, I think that we can look at the design of bridges as an example. So usually the first thing that we have to find is who will use the bridge. So we have two locations, they have an obstruction between the two of them, and we want to actually connect the two locations with this link that is the bridge. So who will use the bridge is the first question. So pedestrians or vehicles or very heavy vehicles. Then the other question is how long is the distance that we have to cover, and also do we have any problem with the river traffic? So for example, we can have this type of bridge that you see can cover some length that can go up to 300 meters, but they don't have any elements going, you see, into the river. And then we can have this other type of this bridge that is quite big, right? So can cover very long distances, but has these elements that somehow can create problems to the traffic inside the river. So you understand that we have different solutions. We have to look at the best one. The other thing, the most maybe important question is what is our budget? Because if we look at a very simple solution, this will be cheap. If we look at something that is a little bit more complicated than the one that I showed you in the beginning, this is going to be more expensive, but maybe still feasible. And then if we go to the real exciting one, right, it's very expensive. So again, we have to find the best solution, not just because we want to protect the environment, the river traffic, but also because we want to find the best cost, so the balance between safety and price. I found very interesting an example to show you an optimization, that is the Thames Barrier Bridge. So we have a problem here. If you look at the map of London and you think that this is Tower Bridge, you can notice that if you look at the east side of Tower Bridge, we don't have any connections between the two sides of the river if we don't go up to Dartford. So actually we have a gap of 20 miles with no connection. So we want to solve this problem, for example, with a connection that will be used by pedestrians and cyclists. And so we have this problem and we have to solve it in order to have a bridge that will be used by many people so we can justify, the cost. We want a solution that is cost effective. We don't want to actually have any problem with the river traffic, and we want to be environmentally friendly. So what the engineers did, they looked closer to the map, closer to Tower Bridge, and they found out actually that on the east side, we have a structure that is the Thames Barrier. So these barriers that can actually protect the City of London from flood risk. So why is this interesting? Actually, what they are suggesting is what you see in this video here. It's a structure that is still not in place and is still under a proposal, phase. But why this solution looks very nice? Because what we can do, we can use the existing structures of the barriers to build the parts of our bridge. The bridge can actually be only for pedestrians, so it can be movable, okay, because it's quite light. So this means that it will not have problems with the traffic in the river, and also the height of the bridge will not be so high, so the bridge will be very accessible to pedestrians. Moreover, by using already the existing structure, the cost will go down, and also we will not really add too much pressure on the river basin. So actually, we will look at an environmental friendly solution. So this is what we do. We look for an optimization of the solution when we have a problem coming from users, from clients. So if this is what we do on daily basis, then we have more bigger, let's say, challenges when we look at natural hazards. So all the events that are coming from nature and that can actually hit our structures, can hit ourselves. So what you have here now in front of you is a map of the world. If you use the website that Panos was actually giving you, and then I think will appear now at the bottom of the slide again. So if you go on mentimeter.com and you actually enter the code you have here, 48798271, you can actually see the same map that you have also on this presentation. And what you can do, you can start picking up the best location that you will select if you will decide to move to another city, to another continent, to another country, or also if you want to go somewhere for a very long holidays. While I will go on with the slides, you can continue voting, and then I will have a look at your answers, and we will see who will be actually affected by earthquakes or tsunami. So if I show you now the same map, but now with some colors, okay? So in this map, what you have, of course, the world, and also I will ask you to focus the attention on the yellow markers. The yellow markers are telling you where we had earthquakes in the last decades. So I think the first thing that you can notice is that some areas are just gray. They don't have any yellow markers, right? So we can say that they are earthquake free. A very interesting case, I think, is the United States, right? Where you see the East Coast free of events and the West Coast instead hit by several very frequent events. So what we are learning here is that the earthquakes cannot happen with the same frequency all over the world, and some areas are really earthquake free. Instead, we have to be very careful if we move to a place where we have a lot of these yellow actually markers. So another thing that you can notice is that in this map, I'm giving you also some blue lines. So the areas that are actually inside these blue lines are called plates. So if you notice, actually, the yellow markers again are all located along these blue lines. These blue lines are actually so the border of these plates. So we are learning also that earthquakes are located in some specific countries, locations, and that they happen along these blue lines that we call the boundary of plates. Let's see how this happens. So if we actually look at the layers we have in our planet, so I will ask you to focus your attention on the left side of this figure because I think it's the easiest one. What we have the center of our planet, its core, high temperature, fluid material, then we have mantle, and then we have the crust. So the crust, the continents, so the continental crust that has a thickness up to 70 kilometers, and then the oceanic one with a thickness up to 7 kilometers. So now what we have that the outer part of our planet is not just one simple block, but actually is divided in these plates, the one that I was showing you in the previous slide. We have 15 plates, continental and oceanic, and these plates actually they're not fixed, but they're moving. They're moving because of the movements we have in the mantle. They're moving very slowly, like for 10 centimeter per year, but they are moving. They are changing the geology of our continents. And because of the motion, at a given time, what can happen, it's like they can create a rupture, a fracture. They can kind of crash if you want. So because of this rupture we have inside this part of the planet, our Earth, actually will be a release of energy. The release of energy will actually be our earthquake. So what we can feel as a shaking. So something like that will happen. So a rupture inside the soil that will generate energy that will travel in the soil and hit us and hit our structures. So what we have is that in this point, you will have, in a given point inside the soil at a given depth, you will have this release of energy. We usually say that the release of energy is happening in one point, and this point is called hypocenter. But when you actually listen to news about earthquakes, they usually tell you what is the epicenter of the earthquake. This is because we usually refer to the projection of the hypocenter on the ground surface. So if you want, the epicenter is the point on the ground surface that is closer to the hypocenter. So when we have this release of energy from the hypocenter, this energy will be released. So actually you can imagine these waves traveling inside our soil, and when the waves reach our buildings, we will actually feel the earthquake. We will experience the shaking. Now, what we can also understand from this picture is that if we are very close to the epicenter, the seismic waves will reach us in a very short time. And this also means that they will be very strong. If we move further away from the epicenter, the seismic waves will travel a lot during in the soil. And this means that they will kind of lose something. They will lose energy. So actually, at the end, the seismic wave will be less severe, less intense. The earthquake will be less destructive. So this is, I think, something very important, because now when you hear about the earthquake, you will also pay attention to the distance between your location and the epicenter. Another thing that I want to stress here, because it will be very important for the next slide, is that these seismic waves are different. Now, the only thing I want you to remember is that we have two main seismic waves. The seismic waves that are called P waves, that I'm putting here with a smile because they are good waves. They are actually not creating damage to our structure. Instead, we have the S waves that are very disruptive. Actually, they're very dangerous. They can actually put a lot of strain and deformation to our soil and so to our structure. So these are the responsible of all the damage we see after an earthquake. Another thing that you are always, reading about when you have an earthquake is the magnitude. So how strong the earthquake is. So we know that when we hear magnitude 7, 6, it's a big number, right? But what this number means and how can we understand the power of this event? So in this slide, I'm just showing you the equivalent in energy for each level of magnitude. And I will give you some examples. So in this slide, I will give you the energy release as an equivalent in kilograms of explosive. So for example, when you hear that you have a magnitude 3, this means that you have an event that is quite frequent. We have around 100,000 events per year with these magnitudes. And the released energy is, as showed here, like a large lightning bolt. If you move to a magnitude that is 5, you see that we have less events, only 2,000 per year. And now the energy is becoming big because it's comparable to an average tornado. But let's just move one step up from 5 to 6. Look, the numbers is decreasing a lot, so only 200 per year, and the energy released is comparable to Hiroshima atomic bomb. So what again we are learning here that the magnitude is very important, and small changes in the magnitude can make a big difference in terms of power of the earthquake, so how destructive the event can be. So for example, if we have a magnitude 7 earthquake, this will produce 32 times energy that is 32 times larger than an earthquake to magnitude 6. So this is very important as a data when you listen about news of earthquakes. So now if I go to the slide with your answer, okay, very good. So I can see some of you are on the east coast of the United States, so they're safe, but I can see some of you in New Zealand, some of you actually in Turkey, and some of you in Mexico. So if you remember the slide I was showing you, actually all these people, if they live there, they most likely will experience this event in their life. So actually, if you live there, you really need to know how to be safe during an earthquake. So it's actually time for a new question. So same code for Mentimeter, same actually, if you stay just in that same website, you will see now popping up another question that is asking you about safety for earthquakes. So let's say that you are in a location and actually at your location you are experiencing this event, this earthquake. So what do you do? So you have these different options. You can decide to go out as soon as possible by using the stairs, go out as soon as possible without caring about the building where you are. You stay outside where you are, for example, in open space like a garden, or you want to go out as soon as possible, so you will use an elevator or lift. Another decision is just let's stay inside and wait for the earthquake to end. So you will protect yourself under a table, under a door, or maybe you will just remain on the sofa as in this picture, or actually you will decide to go in the middle of the room because you think this is safe. So please go on Mentimeter, use the same code, and you will be able to answer the question. And I will have a look later to your answers to see who did well, who didn't. Actually, someone who can also a little bit cheat because I'm giving you also the answers here. So you will see that actually only 3 of these options are good. Let's see why. The first thing is that really during the earthquake, you don't have to rush outside. You have to wait for the shaking to end. So if you go out, you will actually be in danger because maybe some parts of the building are falling down or maybe some vases, some tiles. So it's very dangerous. You should stay inside. If you are in an outside in a very big space, that's very good idea to stay where you are because actually you don't have any danger coming from the ground, and the elevator is not a great idea. You don't want to use anything that can stop working while you're using because of the earthquake, because you don't want to remain stuck, right? Instead, if you stay in home, you have to be careful because there are also some dangers coming from the home itself. So for example, it's good to go under a doorway, a table, a very strong one. So a good idea to think about it if you're buying furniture. And staying on the sofa is not maybe a great idea as well as in the middle of the room, because again, things can fall and hit you. In the case of the sofa, if you remember, we had a bookshelf, right? So very dangerous for your safety. So these are the main things you have to think while experiencing an earthquake. Of course, if you are not panicking too much, you have the time really to realize that something is happening. Okay, you have to be safe during the earthquake, but actually it's a great idea to be safe before the earthquake. And actually the fact that you are here tonight, listening tonight to us, is a great way to become aware of earthquake safety. And you have to be careful also after, because there, for example, you can have additional hazards, for example, fire explosions due to toxic or inflammable materials. So you have to be careful before, during, and after. I'm just giving you a website from the Red Cross in the United States that actually developed an app that you can download, and they will actually let you know if there was an earthquake close to you, and also you can use this app to let them know that you're safe or maybe you need help. So you see that also social media and smartphones, smart and tablets are helping us to improve what we do about earthquakes. A very, very common question that we always hear is, can we predict earthquakes? The real answer is no. But what the researchers did is actually they developed a system that is called the early warning system. This system is actually able to warn people when after the earthquake already occurred, but few seconds before they experience the actual shaking. How this happen? So if you think this cross here is actually your hypocenter, the waves will start travel, right? So the P waves, the good ones, are actually faster than the bad ones. So what we'll have is that a building can actually experience first the good ones, and then it will be destroyed, damaged by the bad ones. So if we put some sensors that are able to catch the P waves, we will have some seconds, the difference in terms of arrival time between the two waves to warn people. We are talking about really few seconds. So for example, if you're very close to the epicenter, you actually will have a few seconds, like 2-3 seconds. But if you are far from the epicenter, you can actually have up to 10 seconds. So think that now you have your phone, you receive this warning, an earthquake is happening, and you have 10 seconds. We have a countdown. So think what you can do in these 10 seconds to actually be safe during the shaking. So actually what you can do and what we can do is actually warn people and also try to find a safe place, drop dangerous things that we are doing, don't actually stop driving if you want. And also what actually the authorities can do, they can stop transportation, they can stop activities like surgery, and they can also help if you want the emergency responders, because for example we will open the gate of all the firehouses so they will be able to go out and help the people that are actually in danger. So this is what I wanted to show about earthquakes, because before leaving to Georgios, I want just to tell you that usually when you hear about an earthquake and the earthquake is happening in the ocean, in the sea, you think that this will generate a tsunami. But this map is actually showing you the location of all the tsunami in the last decades, and only the yellow and the black the orange and the red ones are the ones that really were destructive. So what you can notice, actually, again, they are localized in some areas. For example, we really don't have many destructive and so severe tsunamis when we look at Europe. Why this happens? Actually, this is due to the fact that tsunami is only happening when the magnitude is very strong. So only when we have a magnitude larger than 7.6, we actually can think about a tsunami that can be dangerous, close to the epicenter. And also if we look at magnitude larger than 7.9, you can look at something that can be dangerous also for a broader region. And also the tsunami can only, usually it's more likely to happen when we have this kind of motion inside our soil, so between the plates. It's less likely if we have instead this kind of motion that, if you want, can be horizontal. So that's the reason why we actually don't have many tsunamis in Europe. So the last thing is, remember that you have to be safe also during tsunami. So you have to be careful if you know that there was an earthquake. You look at the sea, you listen to the noise coming from the sea, and you have to leave the coast as soon as possible. vulnerable. And after the tsunami, you don't go back to the coast. And also you warn people, you look after people that are vulnerable. And also you don't eat food that was actually in contact with the water due to the waves, because this can be contaminated. So this is actually what I wanted to show you. So now I will leave the floor to Georgios. And so it's time for me to enjoy my beer. And Georgios will tell us if we can actually bring it to the moon or Mars.
Thanks a lot, Marianna. Yes, let's reach to that conclusion in a bit. At the moment, I think by now, most of you are wondering why we have used the picture of the moon for a talk that has to do with structures and safety. So I think after this section, you will realize why. The first thing I need you to do is go back to Mentimeter, put the same code, and try to give me your opinion about this question. What can be, in your opinion, the biggest challenge for designing off-Earth structures? For example, can it be rocket fueling or docking, extreme temperatures, aliens, spinning of the planet or the moon, partial gravity, lack of communications, perhaps ground motions, tsunamis that Marianna mentioned, radiation, meteorites, or limited transportation space. You're not going to have so much time, but in the meantime, I'll try to give you some context. So, next slide. Thank you. So this is a question posed several years back. Can we become multiplanetary species? Of course, I'm not here to give you an answer, but try to tell you that, for example, we have the private sector with huge companies like SpaceX, Boeing, and Virgin Galactic, amongst, of course, many high-tech, high-end startups, together, of course, with federal agencies like NASA, the European Space Agency, UK Space Agency, countries like Israel, China, India, United Emirates, and so on, that they're really pushing the boundaries. And actually, they're boosting space exploration, space resource utilization. And I think a couple of days ago, we had a very nice complimentary talk in the Pint of Science about space resource utilization and mining, or even space tourism. So, next slide. Of course, this is a huge project, and it involves a huge interdisciplinary collaboration. We are just humble civil engineers, so our focus is just on designing and building as safe as possible structures on the moon or on Mars at this point, which is still pretty exciting, or the first extraterrestrial structures. So what can we see in this photo here? Except this amazing view, sorry, not the previous one, except this amazing view of the Earth, we can see the lunar surface, the lunar soil, the regolith, and of course we can see potential here. Of course, don't worry, we're not going to hide your view, but we will try to safely and in sustainable way utilize indigenous material for building this structure. Now, next one. By now, Marianna, do we have any answers on Mentimeter?
Yeah, we do. We have a lot, actually. So the winner is extreme temperature. And then
good.
we have radiation meteorites, yes.
Spot on. I think it's perfect because
and then
here
some
you can
also I have to mention rocket docking.
Yes, it's not exactly a very direct challenge that we need as civil engineers at least to address. But however, spot on. Thank you. Very good answers. Here I'm just summarizing a few of the challenges that we need to face. So we might have no or very thin atmosphere, depending on whether we are on the moon or on Mars. And that creates several issues. The first one, for example, is that we have 3 different types of radiation to shield ourselves from. And not only ourselves, but only critical assets, robots, energy fuel tanks, and so on. Solar wind, solar flares, cosmic rays from all over the universe. We might have reusable rockets for transportation, but I think Elon Musk is working really hard on this at the moment. But still, we would have a very limited space and costly transportation from Earth. Another huge factor is partial gravity. I think Marianna mentioned before, for bridges, for example, our biggest enemy, let's say, for long spans is gravity, is weight. So you would think that partial gravity would be a beneficial factor. Well, you will understand in a bit that in our case, it's a destabilizing factor for structures, for our kind of structures anyway. And of course, it's very bad for human physiology and functioning as well. And of course, another thing is that we should make our structures as resilient as possible against extraterrestrial natural hazards, like ground shaking from moonquakes or Marsquakes, or even meteorite impacts. And of course, as you said, extreme temperature fluctuations that we can have even 100 degrees of Celsius difference between day and night. Thank you. Let's focus a bit on the hazard aspect, and especially the ones that have to do with the ground motion shaking. So during the Apollo missions from 1969 to 1977, it is 8 years, they had installed seismographs at 4 different locations, which is fantastic, and it is fantastic that we still have data that we can use from these seismographs. However, we as civil engineers it's not very easy for us to use these, not very useful data because they were not designed really for us. And also these sensors were very, very far away from major events that we had recorded. However, moonquakes, for example, we know that they last for too long. They have very long durations. They can last up of the order of magnitude of hours or so, compared to typical earthquakes that Marianna was explaining about, that they can last for up to 1 minute, more or less. Now, next one, we also know, thank you, that we care about these events because even in this tiny 8-year observation period, look at this yellow circle. Inside, you see these little spots. These are events, shallow moonquake events larger than 5 magnitude. So 2 things here. The first one is that this can really produce significant accelerations for our structures, number 1. And number 2, we should be expecting in longer term larger events, which is a bit frightening. Moving on, except, of course, moonquakes, we should care about. No atmosphere means perhaps, meteor shower crashing on the lunar surface or even on the top of our structure. But the probability is not that big. However, for a meteorite to crash relatively close to the structure, less than 100 kilometers, is a good probability. So it crashes in the soil and produces these shock waves, seismic waves, generates seismic waves, propagates and shakes the structure, accelerates it. And this is a different type of hazard for us that we need to account for, of course. Next one. Thank you. Now, in the past, there were thankfully many engineers and researchers proposing different concepts for our structures. Now, what I need you to think about and keep from this is that we have 2 different types of structure. The first one has to do with creating shielding structures, long-span shielding structures, serving like storage facilities for protecting us from extreme radiation. And the second, habitable modules that we can live inside. So now, some concepts combine both. For example, on the left hand of your screen, Malan Chowdhury proposal, where you can see the regolith infill for protecting us from radiation, supported by a frame, supported by a Kevlar surface that can get tension from the atmospheric pressure inside. So imagine basically, in order for us to live inside, we need to have like an internal pressure, because outside, of course, there's no pressure from the lunar atmosphere, the non-existent lunar atmosphere. Now, furthermore, the second type of structure we can have on the top right of your screen, this inclined fiber inflatable structure from Harris and Kennedy, or a bit below, a bit more sophisticated flower-shaped plum view of the inflatable structure from Borin and Fischelli, and even much, much before, from Novak et al., this pillow-shaped inflatable structure with these compressed modules. However, we have this more modern, let's say, a proposal from ESA, the Moon Village, where you can see this beautiful, I think, on the top, on the bottom left part of your screen, this beautiful rendering, where it consists of these 4-story structures. And within this 4-story structure, scientists or astronauts can actually sleep, live, interact, exercise, and work, basically. And within the walls of this structure, there is this regolith covering from extreme radiation. And we want to understand how and whether this can be resilient enough to the aforementioned natural hazards. Now, going back to what we know, we've seen this this image before, and here we can basically see the lunar regolith. And we know that we know the composition of it, the chemical composition. I'm not going to go over this, of course, because also I'm not an expert on this. However, I should mention that a major player is silicates, more than 40%. We have aluminum and iron oxides together, close to 30%. Unfortunately, we have until now very few samples back to Earth, and therefore we had to come up with some artificial simulants in order to understand its behavior. Same thing for the Martian regolith. More or less, of course, it has differences in the composition, but more or less same things. Aluminum and iron oxides together, less than 30%. Unfortunately, no original samples brought back yet, but we still have the InSight mission, ongoing mission there, Perseverance rover, and the Chinese rover, I think, it landed. So we're working basically with simulants, and here you can see our photos. When we first purchased the first MMS and MMS1 and MMS2 simulants from commercially available from Martian Garden, and we had to test it in order to understand from a geotechnical point of view, that's how we call things that related to soil, to understand how strong our soil is and how confident we can be building on this. However, the basic idea is how we can really utilize the regolith in order to create structural materials out of it. I don't want to bore you with a lot of graphs, but just want you to know that we have two different main approaches here. The first one is compact as much as we can regolith and create bricks out of it, or we can have additive manufactured regolith with or without additives. Now, in this plot, you can see here, for example, the strength of these very, very, very tiny bricks. Cho et al. Created very tiny bricks and tested to see how strong they are. And we get values comparable to clay bricks or even reinforced concrete, which is amazing. And so we, of course, with our fantastic compare panos, we try to do the same, but larger scale. So Pano, can you, because we see your hand here, can you tell us what we're looking at?
Yeah, we have to realize that the raw material is just dust and soil, and we want to build out of it. So we have to stabilize it with no cement, no any chemical binders, nothing we can bring over from Earth. Not even we cannot even use water, as the people in the Stone Age were using to make clay. So, as you said, we have applied some mechanical compression, a few tons of compression over a few square centimeters of an area, and then we also tried some combinations of temperature, some temperature combinations on these tiny biscuits, and this is the best we could do up to now. So you have to start from small, even if you're thinking big. So we started from small Lego bricks because all of us were very good at it. A few years ago, we were building amazing stuff with Lego bricks. So this is an ongoing effort to see what we can make out of this material. One of these efforts you can see there, we used temperatures higher than 1150 degrees and we melted it completely. This glass type material you see over there was red Martian dust, and now is a broken glass. That's all from me.
Thank you very much. So going back, because yes, this is the material, but let's go back to our concept, right? So we decided to focus on these long span shielding structures that can serve as storage facilities for critical and valuable assets, robots and fuel tanks, or even future habitable modules made from regolith. And these needed to be resilient to hazards. So we got inspired from these ancient Egyptian Ramesseum adobe vaults that are there for thousands and thousands of years. They're definitely durable, resilient, and low cost. And on the right-hand side, you can see two very nice concepts from two very big companies, Foster & Partners and Hassel, very nice concepts on how we can develop this. However, we as structural engineers, we need to make them stand. And in order for us to do that, we need to have in mind two things. The first one is go back to the past and understand the problem of sizing the thickness and material use. How much material do we need for these arches, like in ancient Greece, or this beautiful arch river bridge here? How we can use less material and still withstand the loading that we should expect. And the other thing is the geometry. What kind of curve is the best to describe what we want to do? So the famous scientist and engineer Robert Hooke, in his famous anagram, he stated, as hangs the flexible line, so but inverted will stand the rigid arch. So basically, he defined this ellipsoid curve or the catenary curve. Architects are very familiar with that. It symbolizes basically the best geometry for carrying out self-weight only. However, ourselves, we used other geometries as well. So here you can see semicircular, parabolic, catenary, and we went a bit medieval, and we tried Gothic style as well. So in the first row, you can see, sorry, Marianna, one back. In the first row, we can see the different geometries with withstanding self-weight and a lateral acceleration of 0.3 g for those of you that understand. This is 30% of its weight. In the second row, much thicker arches because they need to withstand 60% of the weight, pushing it laterally. So then we thought, hold on, why we don't go to more extreme geometries? Because what to restrain ourselves, since we are not constrained by any masonry construction process over there. Technology definitely points out towards large-scale additive manufacturing, so we are flexible to manufacture any shape we like. And of course, we have sophisticated computational tools. So we came up with this blue, weird, varying thickness arches through a form-finding algorithm, having us see the arches, these gray ones behind, like semicircular, parabolic, and catenary. So basically, these blue arches, they can withstand the same loading with the gray ones, but we can use much less material. For example, in some extreme cases, we can save, I think, up to 60%. And of course, we further enhance these shapes using finite elements in order to avoid pinching areas, what I used to call them muscle arches, like me in this photo several years back. Not. So then we need to move to 3D. So this is 2D or a representation of an overground tunnel, if you wish. But then we can move to more complicated geometries. However, a huge factor that we need to take into account here, look at this little guy. His mass is 56 kilos. But on Earth, he weighs 560 newtons, while on the moon, he weighs 1/6, around 90 newtons. So our structures weigh less on the moon. So this is a destabilizing factor for these arch-based structures. However, the mass is there. And the mass is there means that its property, inertia, is there. And this means that if the structure accelerates, this inertia will produce forces that we do not want. And we still need to find a way to protect our structures from these forces. So in order to do this, we have to focus a lot in dynamics and understand the dynamic behavior. And in order to do that, we need to employ some experimental work. So 3D print our samples and put them in a centrifuge box, spin them in order to simulate low gravity environments, and shake them at the same time with some input ground motions coming from moonquakes or Marsquakes or meteorite impacts, record their behavior real time, and see what we can do. So that's all from me at this point, and we will show you now a fantastic video produced by Hassel that I think shows very nicely what we're trying to achieve on Mars, and I fully agree with this proposal.
Here it goes.
Half a century ago, we took our first step on the surface of the moon. Today, there is renewed passion to explore for our next human endeavor. Mars, the red planet, further than any human has ever been. We face many challenges: remoteness, no livable atmosphere, high radiation, dust storms, and extremely low temperatures. Before any humans set foot on Mars, we must first design a protective shelter. We will protect our astronauts from radiation with a thick 3D printed shell structure using Martian regolith, which works great in compression but does not perform well under tension. To overcome this shortfall, we have chosen to construct the pressure-retaining parts of the habitat from lightweight inflatable pods. They will be made out of high-precision engineered composites that are prefabricated on Earth. Their elliptoid geometry will be able to mitigate the pressure differences whilst optimizing spatial planning. To create the base on Mars, we will use a two-phase approach. In Phase 1, an ecosystem of 3D printing robots will arrive months in advance of any human explorer. They will construct a protective shield for the base by adopting a modular robotic swarm strategy, a plan that allows for redundancies and enhances the odds for success. Intelligent autonomous robots will have interchangeable roles, from battery storage to scout rovers, logistics to excavational, and even 3D printing units, all integrated with multiple cameras and sensors for navigation. They can reconfigure themselves for a multitude of purposes, ensuring prolonged usage beyond the initial build phases. The smallest configuration is the one-wheeled scout rover that uses ultrasonic scanning to analyze the Martian surface to determine the best regions for obtaining optimum regolith. The digger receives the location coordinates and then excavates the Martian soil. It then delivers the payload to the refining assemblies. Here, large chunks of Martian regolith can be processed down to a finer grain and then delivered to the melter robots in situ. They then use concentrated microwaves to melt the regolith and extrude through the 3D printing nozzle. The shell is autonomously 3D printed, layer by layer, over several months by the robotic system. In the next phase, the first astronauts arrive with the habitation units, equipment, and supplies. The robots now take on their second life roles to aid the next phase. They come together to make flexible mobile platforms that can carry the payload from the loading zone to the base. The convoy begins its journey across the Martian surface to the habitat site. The build commences with a connector module placed underneath the protective shield and ready for inflation. The module then unfolds and self-inflates into its final form. The habitation units are then placed into position and sequentially inflated to form the completed pressurized environments. The circular layout of the habitat ensures continuous accessibility of the habitat in the event of a catastrophic failure. Each connector module houses 3 integrated environmental control life support systems, delivering essential services like power, water, data, and oxygen to all the habitation units. A circular conduit delivers these services to multiple endpoints in each pod. The base will be remotely powered by 2 nuclear kilopower reactors and a solar farm, located a safe distance away from the base. In the next stage, the astronauts will construct and install a flat-pack, rail-based racking system capable of connecting to the distribution system, enabling spaces to reconfigure according to their spatial needs. This modular and radical design principle has been adopted for all the habitat pods, ensuring multi-use, reconfigurable environments. A Martian base should not just be a habitat. It is home for the astronauts. Each pod expresses its own identity, quality, and character. A highly functional design which places the human experience at the core. Spaces include a state-of-the-art research laboratory, a hydroponic greenhouse, a fully equipped workshop with digital fabrication facilities, the sleeping quarters with gym facilities, and immersive virtual reality platform. We believe that the key to success of human habitation on Mars is the health and well-being of its residents. Creating a place where work, life, and living combine holistically to ensure they feel connected to each other, to themselves, and somehow to their distant home.
So Georgios is on mute.
Sorry, we came to an end. Yes, Thank you. Here you can find our links to our websites with information about us and our research. Yeah, and that's it. Thank you. I hope you enjoyed this, and we're happy to accept any questions.
Thank you very much.
Questions times then it is. Unfortunately, Georgios, most people would like to visit Earth first, so we have questions about safety in earthquake-prone areas. So what do you do when you are driving and you think an earthquake is coming, or what do you do when you are surfing and then you feel that a tsunami is coming? Is it better to go out into the coast and run on higher grounds, or just drive your that's a question that Georgios could answer as well as an experienced surfer. Or you drive your board in deeper waters. So that's a set of questions for you, Marianna. And there is a question for you, Georgios, about, it's a more technical one. What is the best strategy? Is it possible to test a structure simulating actual conditions here on Earth, or we can just model it, applying the best of our theories or models, and then set it up there, hoping for the best?
So I can start with the car. So as I said, for the tsunami, the best thing to do is actually to stop the car, stop driving during an earthquake. This is for different reasons. The most obvious one is that you know that an earthquake is happening because you realized it, so you might actually experience some, anxiety, some panic. So you will not your best, position for driving. The other thing is that actually the shaking can cause accidents, and in some cases this is not that common. But for very strong earthquakes, actually the road itself can have damage. Think about a bridge, right? So actually the best way maybe is to stop where you are, stop driving. About the tsunami, I'm not an expert, surfer like Georgia, so he will add something for sure. but I will say that when we think about boats, if you are, offshore, you are away. So yes, you go further offshore to be safer. But if you're surfing, I don't know how far you are from the coastline, and if you are hit by the tsunami wave, we're talking about a strong one, but a big one. So this means that you will actually go inside the coast, maybe hitting buildings, materials. So the wave will actually, bring you inside. So this can be very dangerous.
And
That's why you have to be safe, because in locations where tsunami can be very strong, think about Japan. If you visit Japan, you actually walk around along the coastline, you will have a lot of signs, a lot of warnings telling you that if you hear a specific sound alarm, this means that tsunami is coming. So this will give you the time to actually go back and find a place on an elevated area, maybe upper stories of a building, to be safe. So I will say you go out.
I would fully agree with what Marianna is saying about the tsunami one. However, I would just like to point out, if you are just surfing, totally you should get out and as fast as possible go to higher ground, because you will end up.
If you are in the very deep waters, you will most probably won't realize that the tsunami just passed you, because it is a very low amplitude but very fast traveling wave. So possibly you will never realize that it happened. But you need to be
the experience of surfers.
Except if you windsurf, on the other hand, and there's strong wind at the same day, so you will definitely continue windsurfing for sure. Don't go out. Now coming to the other question, very nice one. Thank you. Well, that's actually something we were thinking. Yes, we think we can test structures for the moon or for Mars for different gravitational acceleration environments. Whilst on Earth, how? Not some extreme testing like a jump to a plane where, simulating low gravity by falling down and so on. But through this centrifuge spinning, as we said. So scale down our structure and spin it with the proper spinning acceleration in order to simulate the exact gravitational acceleration level that we want to reach. So we hope that by doing this, we can get the correct results, and wait for a couple of months and we will have the answers for you. So centrifuge is the answer, hopefully.
Excellent. I don't think we have time for another question, if there is any last-minute one.
Maybe I can take 1 minute really, because I was looking at the answers about what do you do during an earthquake. So, okay, the winner is you go under a table or under a doorway. So great. So very well done. I have some people actually saying that they will run out by using either the elevator, the stairs, or just, trying the way out as soon as possible. So we say that this is not the safest one. I hope that this will help you with your decisions in case you ever experience an earthquake.
Great.
So our time is nearly up. Any last comment from you, Georgios?
No, I hope you continue surfing and that hopefully, one day we will experience during our lifetime the first extraterrestrial habitats. And don't drive while experiencing it. Thank you.
And it's very interesting to see that some people want to just stay in UK. Many. So maybe they saw the map without earthquakes.
Not necessarily. There is a seismicity
Of course, there are other
in
reasons.
place in many areas. There
I just
was one
noticed
in,
nobody's going to Italy, so
was
that's
a-
why I was a bit disappointed. So I think that's it from us. Thank you very much for joining us. It was a pleasure. I hope you learned something and also enjoyed. So enjoy the rest of the evening and
Thank you very
goodbye.
much.
Cheers.
Bye-bye.